Your phone is dead. The room is dark. And instead of crawling around on the floor hunting for a cable, you simply set it down on a small disk. A gentle light appears. The battery starts filling. No plug. No contact. No connection of any kind that you can see or touch. What you are watching is not a modern invention. It is a 130-year-old idea that the world was not yet ready for, finally coming home. You come home exhausted. Your phone is sitting at 1% battery, the kind of critically low number that produces a specific, low-grade anxiety that anyone who has ever needed their phone in an emergency understands immediately. But instead of fumbling around in the dark for a tangled cable, searching for the correct end, trying to orient the connector correctly in the dark, you simply set the phone down on a small disk on your nightstand. A small indicator light appears. The battery icon on your screen turns green and begins filling. It feels genuinely like magic. Invisible energy somehow crossing empty space from a plastic pad directly into your phone, with no wire connecting the two, no pins making contact, no physical bridge of any kind between the charger and the device being charged. But this is not magic. It is not even particularly mysterious once you understand the physics behind it. It is the end result of a scientific principle identified in the 19th century, pursued by one of the most ambitious and ultimately tragic inventors in the history of technology, abandoned for nearly 100 years because the supporting technology did not yet exist, and finally delivered to the nightstand of practically every household in the developed world in the form of a quiet, unassuming plastic disc. To understand the pad sitting on your desk, you have to go back not to the 21st century or the 20th century, but all the way to 1891, to a laboratory in New York, and a man with an idea so large that it ultimately destroyed him. In 1891, long before smartphones existed, long before commercial electricity was available in most homes, and long before the modern power grid had taken its current shape, a Serbian-American inventor named Nikola Tesla stood in his New York laboratory and demonstrated something that most of his contemporaries considered either brilliant or insane, depending on their disposition. Tesla believed, with complete conviction, that humanity did not need wires to transmit electrical power. The wire, in his view, was an unnecessary constraint, a physical limitation that engineering ingenuity should be able to circumvent entirely. To demonstrate the principle, he built what became known as the Tesla coil, a device that generated a rapidly alternating electromagnetic field of extraordinary intensity. Using this device, he lit electric light bulbs placed across the room with no physical connection of any kind between the power source and the bulbs. The audience watching this demonstration was witnessing something real. The physics was sound. Power was genuinely transferring through space without wires. Tesla's ambitions did not stop at lighting a room. His ultimate vision was staggering in its scale. He imagined a massive transmission tower, the Wardenclyffe Tower, which he began constructing on Long Island in New York in the early 1900s, that would broadcast electrical power wirelessly across vast distances, much as radio signals travel through the atmosphere. He envisioned a world completely free of power lines, where electrical energy was available everywhere to anyone with the right receiving equipment, transmitted invisibly through the earth and atmosphere from a network of giant towers. The vision failed. Transmitting useful quantities of electrical power through open air over long distances proved to be catastrophically inefficient. The energy dissipated rapidly in every direction, most of it wasted before reaching any intended receiver. The financial backing Tesla needed to continue the project collapsed. He went bankrupt. The tower was demolished. And the world, entirely practically, went back to copper wire. But Tesla's underlying scientific principle was never wrong. The physics he demonstrated in his laboratory was genuine. The idea was simply waiting, patiently, for the technology around it to develop to the point where it could be made practical at a small scale. That moment arrived, quietly and without fanfare, in the early 21st century. The technology that makes your wireless charging pad work is called electromagnetic induction. The name sounds intimidating, but the underlying concept is one of the most elegant relationships in all of physics, and it can be stated in 2 sentences. Electrical current flowing through a wire creates a magnetic field around that wire, and a changing magnetic field passing through a wire creates an electrical current in that wire. These two facts, discovered and formalized by the English scientist Michael Faraday in the 1830s, several decades before Tesla was even born, are the complete scientific foundation of wireless charging. Everything else is engineering. If you were to open up a wireless charging pad, the main component you would find inside is a flat, tightly wound coil of copper wire. When you plug the charging pad into a wall socket, electrical current flows through this copper coil. As that current moves through the wire, it generates a magnetic field in the space immediately above the surface of the pad. The current in a charging pad alternates direction at high frequency. This is critical because a static magnetic field would not produce the effect needed. It is specifically the changing, oscillating nature of the field that makes the energy transfer possible. Now consider your smartphone. Hidden just beneath its rear glass panel is a second copper coil, slightly smaller than the one in the pad, built directly into the phone's internal architecture. When you place your phone face up on the charging pad, you are positioning that second coil directly within the oscillating magnetic field generated by the first. Because the magnetic field is constantly changing, it induces, pushes, electrons into motion within the phone's copper coil. Those moving electrons constitute an electrical current. That current flows through the phone's charging circuitry and into the battery, adding charge. No electrical connection crosses the gap between the pad and the phone. No electrons travel through the air. The energy moves as a magnetic field, and the phone converts that field back into electrical current on the receiving end. The gap between the two coils, typically a few millimeters of plastic and glass, is irrelevant to the magnetic field, which passes through non-conductive materials as if they were not there. This is the same principle at a dramatically smaller and more controlled scale that Tesla demonstrated in his laboratory in 1891. A reasonable question arises at this point. If the charging pad is continuously projecting a magnetic field above its surface, what happens when you accidentally set your car keys on it? Or a metal ring? Or a handful of loose coins? Should those metal objects be heating up, or worse, being damaged? The answer is no, and the reason reveals just how sophisticated modern wireless charging systems actually are beneath their deceptively simple appearance. Contemporary wireless charging operates according to a global technical standard called Qi, a word drawn from Chinese that translates approximately as vital energy or life force. The Qi standard was developed and is maintained by the Wireless Power Consortium, a collaboration of technology manufacturers, and it governs not just the physical parameters of wireless charging but the communication protocol between charger and device. Before any significant power transfer begins, the charging pad and the device communicate with each other digitally. When you place your phone on the pad, the phone transmits a small digital signal, essentially announcing its identity, its power requirements, its current battery level, and its compatibility with the charging standard. The pad receives and verifies this signal. Only after this digital handshake has been completed successfully does the pad begin transmitting power at the level the phone has requested. If you place your keys on the pad instead of a phone, no compatible device sends the required identification signal. The pad detects no recognized receiver, and it does not initiate full power transmission. The low-level field used for detection is not strong enough to meaningfully heat the metal. This communication layer also allows the charger and phone to negotiate power levels dynamically throughout the charging session, delivering higher wattage when the battery is low and the phone can accept it efficiently, and reducing power as the battery approaches full charge to prevent overheating and protect the battery's long-term health. The simplicity of the physical interaction, phone placed on pad, charging begins, conceals a continuous, sophisticated digital conversation happening invisibly between the two devices throughout the entire session. The distance between Nikola Tesla's Wardenclyffe Tower and the charging pad on your nightstand is not just a matter of scale. It is a matter of focus. Tesla's vision was enormous, planetary in scope, unlimited in ambition. He wanted to eliminate the wire from the entire world's power infrastructure simultaneously. That ambition required solving problems that the technology of his era, and arguably any era, could not solve efficiently. Power dissipates as it travels. Targeting a diffuse wireless transmission to specific receivers across large distances while preventing catastrophic energy waste is a problem that remains unsolved today at any practical scale. But the engineers who developed modern wireless charging asked a much smaller, much more answerable question. What if we do not try to transmit power across a room, or a city, or a continent? What if we transmit it across 3 millimeters, from a pad to a device resting directly on it? At that scale, the efficiency problems that defeated Tesla essentially disappear. The magnetic field does not need to travel far enough to dissipate significantly. The two coils can be sized and positioned to maximize coupling efficiency. Modern Qi-standard chargers operate at energy transfer efficiencies of roughly 80 to 90%, genuinely competitive with wired charging in many real-world conditions. Tesla had the right principle and the wrong scale. The engineers who built the Qi standard had the wisdom to find the scale where the principle actually worked.